In this screencast, I'm going to explain the implementation of gradient descent of simple linear regression. First of all, I'm going to walk through those functions required to implement the algorithm. First of all is the partial difference quotient function. It's used to compute the partial derivative, which indicates how function changes when we make a small change in just one of the input variables. And the next is estimate gradient function. It's used to compute the gradient by passing each value in the initial point to the partial quotient function, partial difference quotient function. And the new step function is used to generate the next point based on the gradient which indicates the direction of max decrease. And the Euclidean distance function is to compute the streamline distance between 2 points. In this case, we use this function to check the distance between the current point and the next point. The predicted y function, we use this function to generate the predicted y value based on the provided slope, intercept, and x value. The error function is to get the difference between the actual y value and the predicted y value. Sum of squared errors is to sum all the errors, which is a distance between expected point and the linear model. And the find mean function is the main function or the implementation of the algorithm. First of all, we take an initial point and we set the tolerance and we set a list of step size. The reason why we set this step size to be a list of values, by doing this, it prevents the value bouncing back and makes sure in each iteration the point is moving in the same direction. And within this while loop, we first find the gradient, which will tell me the direction of greatest decrease. Based on the gradient, use the step function to compute the points using each step size in that list. And then we use the main function with input function f as the key to find out the next step, which minimizes the function f. This if statement is to check whether the distance between the current point and the next point is less than the tolerance or not. If it's less than the tolerance, it means we've reached the minimum and the sum of errors is the least. If not, we need to continue doing the above steps until the convergence of the current point and the next point. Next, I'm going to explain the results of each input dataset. First of all, it starts from -4 and -6, and its minimum occurs at approximately 1.2. So the least regression line of dataset 1 is y equal to 2 plus 1x. And for the dataset 2, it started at -7, -1, and it minimum occurs at -1, 3. So the least regression line of dataset 2 is y equal to 3 minus x. For the dataset 3, it started at 0.11, and the minimum occurs at approximately 1.67 and 5.07. So the least regression line of of dataset 3 is y equal to 5.07 plus 1.67x. And for the dataset 4, it starts at -8, -9, and its minimum occurs at 22.94 and 0.9. So the least regression line y is y equal to 0.9 plus 22.94. That's all.